Hey, here's a little video for question 3.3.3 from the book. In this case, we're introducing what's known as a saddle point in two-dimensional systems, where we have an equilibrium point at the center here, and pictured in each quadrant is a typical type of trajectory and how it would behave around a saddle point. A saddle point is a two-dimensional mixture of stable and unstable, where you can see that coming in from the bottom, things want to tend toward the fixed point, but as they get toward it, then they take a curve and they want to go away from it. Again, in this quadrant here, it's like they want to go towards it, but then once they get close enough to it, they take a turn and go away from it. Now, what would cause that kind of behavior? If we look at the rate equations over here, these are actually pretty simple equations to analyze, and that's because they're what's called fully decoupled. A decoupled system is one such that the first variable's rate equation actually only depends on the first variable itself, not the second variable. Likewise, for the second equation, the rate equation for y only depends on y, it doesn't depend on x. And so that's really special about this equation, is that it's fully decoupled. So you just want to write that that's special about it. And because it's fully decoupled, it's actually less like a real two-dimensional system, and it's more like two separate one-dimensional systems. Like, I could just ignore y because it's not involved in the rate equation for x, and likewise for y. I could just ignore x because it's not involved in the rate equation for y. So in addition to being fully decoupled, the rate equations are also linear. And I mean linear in the sense of linearity. Remember that linear equations, when we talk about differential equations, means that it's of the form x prime is equal to rx. And here the r is equal to 1, and here the r is equal to negative 1. So not only are they fully decoupled, they're also linear in nature. And that makes them really special. That actually makes us able to state the full solutions, which is not usual for general systems of equations. But for these ones, we can solve the equations. Do you remember what the solution x of t would be for the rate equation x prime is equal to x? Do you remember what the solution y of t would be if the rate equation was y of t is equal to negative y? We covered that in section 2.7, but I'll leave that answer for the end of the video. That's because in this video, you actually don't need to know the explicit solutions to this differential equation to be able to go from trajectories in the state space into graphs in the time series. You don't really need to know it, but it's just kind of nice. So I'll give that answer at the end, but I would encourage you to try to do a bit of review and try to derive what are the solutions x of t and y of t using your knowledge from 2.7, and then I'll give the answer away at the end of the video. Okay, but the question's actually asking us to draw, I'll just read it straight out of the book, sketch time series for both x and y corresponding to two trajectories. Okay, so I can pick any two trajectories. There's one trajectory here that's sticking out like a sore thumb that I'm definitely going to pick first. It's the easiest one. Which trajectory should I pick first? Right there, the equilibrium point. That is a trajectory. That is the equilibrium point trajectory. And that's going to be the easiest one to pick because it represents constant behavior in time, right? So I'm just going to draw horizontal lines for both x and y for whatever they're represented by this equilibrium point. So what's the value of x at this equilibrium point? And what's the value of y? They're both 0, right? Yeah. So that equilibrium point represents the solutions x of t equals 0 and y of t equals 0 for all time. And so one answer to this question is just simply following along the t-axis and saying x equals 0. And then likewise, just following along again for y, and y equals 0. And those are the equilibrium solutions. That was easy, but you probably want to see me do a different one than that, right? Okay, so how about I pick this one in the first quadrant? And what I do here is pretty equivalently matched for any of the other quadrants. You can see that these trajectories are looking quite symmetric around the saddle point. So let's say that I want to describe this trajectory. In order to do that, I really need to define an initial condition for myself, because otherwise I'm not going to know where to start at t is equal to 0 right here. So I just have to pick a point for my initial condition. Maybe I'll pick this point right here, and I'll pick this as my initial condition for my second trajectory that I've chosen. And the initial condition that I picked right here kind of has a large y and it has a small x. You see it's high up, so it has kind of a big y, and it kind of starts over here, so it's a small x. So I'm going to do x and y separately, but I just want to note where each one starts to start us off. Like I was saying, y sub 0 for that initial condition is up there, and x sub 0 is going to be down there. That's because my initial condition, x naught, y naught, is just a little bit over in the x, but it's a whole bunch over in the y. So it's big on the y and small on the x. Okay, now like we talked about earlier in the course, what you're going to want to do when you go from state space to time series space is that you're just going to want to focus on one of the components in a two-dimensional state space. So if I'm going to try to draw the x as a function of time, I'm going to follow with my finger the trajectory, and I'm just going to think about what's happening in the horizontal component, okay? So I'm going to ignore the fact that it drops down. Forget about that for now. I'm just going to be thinking of whether it moves to the left or to the right. And if it moves to the right, that will mean the x is increasing, so I'll draw x going up. And if it moves to the left, that means x will be decreasing, so I'll draw x going down. Okay? So let's follow it together with my finger. And horizontally only, is it just moving to the left, just moving to the right, or a little bit of both? Just moving to the right. And if it's just moving to the right, that means x is getting larger and larger. And so when I draw my solution versus time, that's going to be my x of t. It's going to be getting bigger and bigger and bigger, because this one is just moving to the right. Okay? Now, likewise, I'm going to do the same thing when I draw my y of t, but I'm just going to be thinking about the vertical component. So I'm going to trace my finger again along the trajectory, and I'm going to think about, is it moving up or down? Now I don't care if it's moving to the left or right, because I'm just talking about the y component. So let's think about it. Is it moving up or down? It's just going down. It's not going up at all. And so since it's just going down, I'm going to have my y of t is going to look like this. Okay? One thing that might be on your mind is, hey, how did you know the shapes as a function of time are going to look like this, as opposed to being more a different shape, like just a straight linear shape or some other monotonically increasing or decreasing function? That's because I know what the explicit solution is to the differential equation. So did you go back to section 2.7 and think about that? Like if I just told you that x had a rate equation, x prime is equal to x, what is the full explicit solution, x of t? It's a linear equation and the r is equal to 1, so x of t is actually, it's the initial condition x naught times e to the rt, but r is just 1, so it's x naught e to the t. Yeah, I kind of knew that, so that's why I was drawing an exponentially increasing function. Same thing for y of t, because it's fully decoupled. The only reason I'm able to do that for this particular example is because it's fully decoupled. So x only depends on x, y only depends on y. That's not usual for a two-dimensional system. But it's a good review of one-dimensional systems, because really, since it is fully decoupled, we just have two one-dimensional systems. X is just listening to x, y is just listening to y. Lucky us, so we get to review one-dimensional rate equations. Same question for y. If I just gave you the rate equation y prime is equal to y, then what would the explicit solution be for y of t? Same kind of deal, right? It's going to be the initial condition times e to the rt, and here r is minus 1, so y of t equals y naught e to the minus t, and so I knew it was going to go down like that. Yeah, The other thing actually that helps me know that y is going to behave like this, asymptotically approaching 0, as opposed to being like a line that just shoots down straight and hits 0, is because you can see that the trajectory in the state space is approaching the horizontal axis, so the y is getting lower and lower, but you know that it's never going to cross the axis completely. It's just asymptotically approaching it. And that asymptotic approach in the y component speaks to the fact that there's a horizontal asymptote in the equation y naught e to the minus t. If I drew a line, if I just thought y was linear instead and I drew a line straight down, there would be no way for me to get out of the fact that a line is going to intersect the axis. But this trajectory does not intersect the line y equals 0, and so likewise, the time series solution should not intersect the horizontal axis for time. So that's just exponential decay for all time. Hope that helps.